Alright, for the posterior for the full conjugate prior, the full conjugate prior, the prior in this part was this, right? So for the joint posterior, joint prior, were decomposed into in this way, right? So what we're going to do is to get a posterior for each of the terms right here. So the joint posterior can be decomposed into these two terms. And if you can notice here, this posterior right here is actually a full conditional posterior of beta given the other parameters, which is sigma squared, which is we have already what we have already derived in the previous slides, right? In the full conjugate and semi-conjugate cases. And if we use a G prior, then this form is known, right? Perfectly known. So this is not, so this term right here, this term right here is not our problem. The problem is with this one. This is a marginal posterior of sigma squared given y. So the marginal posterior, is a posterior where beta were integrated out, right? Were eliminated, which means that this term right here, means it measures the effect, of y, effect of y on the sigma squared, right? Where all the effects of beta were conditional, were averaged, right? So on average, so when we say marginal posterior, so the marginal posterior is a posterior of a subparameter where all the other effects for all the other parameters and its effects were averaged, right? In some sense, averaged or integrated out, similar thing, right? So in order to get this, in order to get this one, we're gonna have to use this one, right? So the posterior of the sigma squared, is proportional to the prior and the likelihood. And since the prior is dependent on our own choices, it is not our problem, but the problem is this one, right? This is the likelihood of a data where all the effect of likelihood of a data where all the effect of beta are all integrated out, right? So, and if you give a G prior for the beta, then we have the posterior with this mean and variance. We're gonna say mean to be m and variance to be v, right? And since this one is also normal, and also this one is also normal, right? This is a G prior, right? So we can, combine these two expressions inside the exponential terms, and for all the other terms that does not depend on beta can be separated out. It will be moved outside of this integral region, right? So we have this some constant right here, and if you also expand this term, then you're gonna see the y transpose y would also escape from this integral equation, right? Integral part, right? So, and at this point, you might see, one might guess, you could notice that, you have to notice that this term is actually a quadratic form with respect to beta and beta, right? And if you see a quadratic form, and if you go quadratic form in terms of beta, and if your goal is to integrate the beta, and if you do not want to, and obviously you don't want to do a vector integration by yourself, right? We're gonna have to use the result that we already know, which is that the beta follows this this distribution, right? So in order so our goal here is to make this part somehow transform this part to be this one, right? Because if that's the case, then this is actually the posterior of the beta, right? And it can be if it is integrated, then we're gonna get a inverse of a normalizing constant of the beta posterior, right? So to do that, we're gonna have to first subtract m from beta and use v. Use v. By use v, I mean if you subtract m from the beta and you rearrange the terms, you're gonna see some complex amalgamation of symbols and all such things, and you're gonna have to write v, to simplify that, right? You can actually do this by yourself, right? I would actually recommend that you do this by yourself, because all such practices can be very come in handy when you are reading some more difficult Bayesian literatures, right? Because the crux, the essence, in my opinion, the essential point of Bayesian inference is a sampling, because in most cases the posterior are analytically intractable, right? It is impossible to do an exact integration, to get the exact form of a posterior. So in most cases, Bayesian statisticians rely heavily on sampling, but you can save a lot of time and computational power required in sampling by some clever tricks, like some clever giving priors and clever deriving posteriors, and a lot of that part involves the Gibbs sampler, right? The Gibbs sampler saves you a tremendous amount of time. And to do Gibbs sampler, we need a full conditional posterior, and deriving the full conditional posterior is always in all cases, it always involves doing some heavy math, right? And if you have done this practice enough while reading the textbook, then I guess it'll be really more easier it'll be easier for you to go through the literatures. Okay, so anyway, after all this toil, right, we get a final form, which is that the likelihood of y given sigma squared is proportional to this one, right? So, what we actually need, what we need indeed, is only these two terms, right? Because using only these two terms, with the appropriate prior, we can easily derive the posterior, right? And but this term right here, it does not depend on sigma squared, but it's gonna be proved. It's gonna prove to be useful in model selection parts. So the SSRG here is actually this term, and it can be summarized right here. So and it can be expressed as this term. So SSR, sum of squared residual of G. My interpretation is the sum of squared of residuals, that is averaged over the entire possible probable betas, whose density is determined by the G prior. So in that sense, if you set a weak prior for the betas, which means you give large values for G, then your SSRG would be very much analogous to the SSR of the beta, MLE, right? The standard data residual sum of squares, right? So anyhow, we have succeeded in deriving a full conditional posterior. So with this term right here, we know that sigma squared given y follows the inverse chi-square distribution right here, and given the sigma squared, we know the posterior of this one, right, which is G prior. So our sampling strategy, so there is no approximation in sampling strategy right here, because as opposed to Gibbs sampling, because in Gibbs sampling, we are essentially approximating the full, posterior with two, full conditional posteriors, right? But in this setting, we can actually write the closed form expression. We actually have the closed form, expression of the full posterior, right? But since the sampling, but this algorithm is just the sampling scheme for these full joint posteriors, right? First we select samples from. First we sample from the sigma squared, right? Sample from the sigma squared, and then give conditional on this sigma squared. We sample from beta, and as a result, we get a sample. Then we get a sample from the joint posteriors, right? So the code here is very easy, right? There's nothing nothing special about this. If you have done, if you know how to use functions like this one, right? And we are no more in R, then in our studio, then you're gonna easily come up with your own code. Uh, there's literally not much to be not much to code right here, just the sampling. And for the final part, finally, we are all geared up, we are all prepared to talk about the Bayesian model selection, right? And for this topic, I'm gonna cover this topic in the next video.